One part of the analysis is to make sure you understand when you do a factor rotation why you're using the principal components analysis. And you choose this because it lets you know the total variance that's explained by those eigenfactors or eigenvalues of the factors and the data that you're considering. And it will help you determine the number of factors that will count for the maximum variance in your data. I'm going to walk you through how to go about doing one of the factor analyses in SPSS. Here's our SPSS file where we have our 38 variables. So we get Analyze, Dimension Reduction, Select Factor. You can reset it because it's always on the last option that you just did. And for my situation, I have to pick all 38 variables because I'm considering all of them. And I want to know the univariate descriptives, the coefficients, significance level, the determinants, the KMO, and the Bartlett's test, the inverse, the reproduce, and the anti-image data. For the extraction, I'm going to go ahead and use principal components. I want a Scree plot. I want the unrotated factor solution. Right now, I'm just basing my eigenvalues on 1 because I don't know how many factors I'll actually get from those 38 variables. The rotation, since I have done my data analysis, I know that they highly correlate in order to be similar trust-related behaviors. So I'm actually going to choose the ProMax method for rotation. I want loading plots and the rotated solution. And I typically keep the maximum number of iterations to 25. For scores, I like to save my variables, and then I use the Anderson-Rubin as a test. And I also like to display my factor score coefficient matrix. For the options, I just make sure I exclude my cases listwise. So if there's any individuals, it will exclude those individual items listwise. I'm going to sort by size. And I'm going to suppress the small coefficients. I actually changed this from 1 to 3, and some will do it as high as 0.4 for a small coefficient. I'll hit OK. Okay. Now, I'm not going to walk you through this entire process because it was just iteration after iteration of redoing the data. But the very first thing I went and did was look at my results here. So I'm looking at descriptive statistics, my correlation matrix, my inverse, my KMO, and you can see I have a terribly low KMO, well below the 0.5 minimum that Andy Fields recommends, because there are 38 variables after all. I look at my anti-image matrices, and then I come to the communalities, and I actually will identify by looking at the extraction any number that is 0.6 or lower, and I'll just remove them in the next analysis. So right here, I'll demo this at least once because I had to go through it several times. It's a long process usually. So I'll go back to my factor. And then what I do is I look at apologize quickly. And I see it's a really low. So I come here, I select apologize quickly as my variable, and I kick it back over into the list of my variables on the left-hand side. And then I keep scrolling down, and I saw that gives negative feedback in private. So I'll move that one over. And then shows bias, and I'll move this one over. And then I see continuous improvement is also a variable that is below. So I'll move this one. Not afraid to speak looks like it's the next one, so I'll move that one. Gives responsibility to the other persons. I'll move that one. And then I'll go ahead and just click OK. Come down here. I see it's improved greatly. It went from 0.414 to 0.745. But I come back to my communalities, and I often find it really hard to read them because they are longer than my computer screen. So I'll come into the edit area, and I'll just stretch these out a little bit and edit the document so it's a little easier for me to read it, and then close out here, and then start looking at my numbers. And if I see, again, numbers that are lower than the expected extraction amount, I'll just come back in and I'll keep removing them. And it's not until you have a good iteration where you're avoiding those low numbers that you choose to stop. I'm getting closer, but let me go back to my data set and just show you, because it took 5 iterations to get this data to show how many eigenvalues and factors I could use. The first thing I want to do is just kind of walk you through all the data that you're going to see produced in SPSS. The top half of this chart, or the bottom half, it's split right down the middle with the perfect correlation, is what you want to look at, because it replicates the Pearson correlation coefficient between all pairs of the questions. And then what you can do is use this correlation matrix to check the patterns of relationships. And in order to conduct an exploratory factor analysis, the variables need to correlate. So the researchers on this project reviewed the correlation matrix to check for correlations that are greater than 0.3 but less than 0.9. And we did the diagonal elements directly after, right here. And it's like the KMO measure, and it just should be greater than 0.5 at the bare minimum. And if your sample is adequate for a given pair of variables, and if any pair of variables has a lesser value than that, consider dropping one of them from the analysis. And the off-diagonal elements should all be very small or close to 0. So that's why you'll see smaller scores like 0.89, 0.3, 0.2, 0.2. That's okay. What you're really paying attention to are these diagonals. And as long as they're greater than 0.3 but less than 0.9, you're okay. The next thing you're going to do is look at your KMO and Bartlett's test. And if you selected the KMO and Bartlett's test of sphericity and the anti-image options, then your outputs will contain the Kaiser-Meyer-Olkin measure of sampling adequacy, and then Bartlett's test of sphericity and the anti-image correlation and covariance matrices. So Kaiser in 1974 recommended a minimum of 0.5 for the Kaiser-Meyer-Olkin measure of sampling adequacy. And the values between 0.5 and 0.7 are mediocre, values between 0.7 and 0.8 are good, and values between 0.8 and 0.9 are great, and then values above 0.9 are superb. So a value of 0.817 is great, and it's well above the acceptable level we need for our sample. Now, Bartlett's test of sphericity will usually be significant right here by seeing that its p is less than 0.05. If it's not, you got a disaster on your hands. And we as a research team use the Bartlett's test of sphericity to verify that the variables correlate with each other, and it's desired to have Bartlett's test to have a significant value less than 0.05 to indicate that there is a relationship between the variables. And for this, when we calculated it, we were able to indicate that our correlations were significant, and we proceeded with our factor analysis and decided everything was appropriate. Additionally, we knew that there were no correlations greater than 0.9, so we believed that multicollinearity would not be a problem with our data. We also checked the determinant of our correlation matrix and eliminated any variables that we thought might cause us a problem, and we were able to double check that the determinant was less than that 0.0005 number that Andy Fields desires. So after we examine the KMO statistics, we need to also look at the anti-image matrices for looking at the individual variables. And Fields suggests that values for these individual variables should be above 0.5. So all of the values for the individual items are well above 0.7. You can see here as it goes down the diagonal. And our research team was really confident that our sample size was adequate for the exploratory factor analysis and that our variables correlated appropriately. So after several iterations of data, about 5 iterations, we were able to identify that the eigenvalues would help us know how many factors. And by default, SPSS uses the Kaiser's criterion of retaining factors with eigenvalues greater than 1. So this table is titled The Total Variance Explained, and it lists the eigenvalues associated with each factor before extraction, after extraction, and then after the rotation. So here's the initial before, here's what it is after, and here's what it is with the rotation. And before the extraction, we see that we had 10 factors identified in the data set, and the eigenvalues associated with each factor represented the variance that it could explain. So the first factor could explain 53% of the variance, the second factor 13.96, the third factor 13.01%. And SPSS then extracts all the factors with eigenvalues greater than 1, which leaves us with the 3 factors we see here. And our eigenvalues associated with these factors are again displayed, and the percentage of variance explained is in the columns labeled extraction, sums of squared loadings, and we see just how much variance each factor will account for. I told you guys how I had a lot of iterations. Well, this is the slide that will show you the table of communalities before extraction. So here's all my variables, and remember that your commonality is the proportion of common variance within a variable. So Fields and Stevens recommend suppressing indicator loads that are less than 0.4 to just assist in the interpretation, and that cutoff just represents loadings with important values. So only variables with loadings of 0.4 or higher in the factor were considered. And once we identified our factor structure, we decided that our variables could have how important each variable would be in each factor. And our sample size can really determine the significance of a factor loading. So Stevens considered a loading greater than 0.7 to be significant for the sample size of 50, which is very close to what we have in this study. And the items that have an orange box around the extraction had factor loadings of 0.6 or lower, so those items were removed from the solution. Then I reran it, I removed these items, I reran it, I removed these items, I reran it, I removed these items, and then this is my final iteration with the number of variables I was able to come up with. So let's talk a little bit about how factor analysis is an exploratory tool, and it really does guide us to make the various decisions you need. You don't allow the computer to make your decisions. So one important decision is the number of factors to extract. We saw the eigenvalues being 3, but to select your appropriate number of factors to extract, you not only look at the eigenvalues, you also need to look at Veliosur's minimum average partial or MAP test and the Scree plot. So Veliosur's map just indicates 3 components according to 1976 Criterion, and then we will run that as a syntax in SPSS, and it will tell you just how many variables it thinks it can have. And you can compare that number to your eigenvalues, and then you can compare it to your Scree plot. So here's the eigenvalues again, and then here's the Scree plot. And with the Scree plot, it's just really important to remember that it's a plot of all the eigenvalues against the number of factors in order of the extraction. So the point at which the Scree begins to denote a true number of factors, you'll see this little slump, and that's when you'll know that that's the number you should select. And it's identified here with 3 eigenvalues, or 3 components. If you see how it drops dramatically to 2, drops dramatically to 3, goes a little up through 4, and then kind of just fizzles out and has a consistent line that's drawn through the slope and shows a change as it goes down. Now the next thing to do is make sure you actually select the right type of rotation, and we can pick from 2 types. We can have orthogonal or we can have oblique. And in the orthogonal rotation, our factors cannot correlate. So our factors are constrained to be uncorrelated. But in the oblique rotation, our factors are allowed to be intercorrelated, which means that correlation values we were looking for earlier were acceptable. So orthogonal rotation often leads to misleading solutions in situations where we know that factors are expected to be intercorrelated. Thus, in most cases, the oblique rotation is preferred because it provides a more realistic representation of how the factors can relate. And if factors in fact uncorrelate, then the oblique rotation will just produce a solution that is the same as the one that's produced with the orthogonal rotation. And if your factors are intercorrelated, then your oblique rotation will yield a more accurate representation of the magnitude of those relationships. So ideally, I've always used the oblique rotation of the 2. Now your oblique rotation is going to return 2 types of matrices. You're going to have a pattern matrix, and then you're going to have a structure matrix. And while the pattern matrix reported the regression coefficients for each variable on each factor, our structure matrix just illustrates the correlation coefficients between each variable and factor. And Fields explained that researchers interpret both the pattern matrix and the structure matrix. So we went from having 38 variables to having only these 10. For our final exploratory factor analysis. And we have 3 factors that account for almost 80% of our variance, and we gave them our own labels. So not only do you need to be able to see how they group, you have to actually be smart enough to know the research to identify the name of the factor. So I called the first factor transparent honest, because it talked about how we don't disclose private information, we don't talk about people behind their back, we take responsibility, we make things happen. I chose relationship maturity because we're open to direct communication about our problems. We address tough issues directly, and we don't break confidences, and that shows a lot of maturity in how we handle relationships with individuals. And then the last one was about developing feedback systems for formal and informal communication. as well as finding out what's most important behaviors are to you. And that's a very individualized, customized focus. So I identified that third factor with that term. Now, factor 1 will help you kind of understand how you will handle tough issues, that we don't bring confidences. We really make sure that we listen before we speak, and we're not allowing any pride to interfere in what we're trying to do, and we're just being appropriate in our transparency and the honesty that we have with our individuals. And with the individual customer focus, that's really about just developing formal and informal feedback systems, and then finding out what were the most important behaviors that individuals like, and then trying to use those behaviors and practice those behaviors when we interact with those individuals. And of course, we also just want to make sure we don't overpromise and underdeliver kind of things, and that we just behave very maturely, of course, with our relationship maturity factor. So you have to be able to define them too. And this is a typical table that you'll see in SPSS. I created it to follow APA style. So you'll see each item, and then you'll see each rotated factor loading. And not only do I provide the exact correlation, the coefficient, the regression coefficient for it, I make sure it goes to 3 decimal points, and then I include the eigenvalue, the percentage of the variance, and our Chromebox alpha, which we'll calculate at the end of the process. We also want to look at the structure matrix, where we say that our variables actually correlate and there's a relationship between them. Well, this table lets us see how that works. So now we know what variables correlate with other variables and by how much. If you have any questions or comments about a factorial analysis, you can check out these references, but I would actually encourage you to download the paper. It's about 10 pages long, double-spaced, and it will walk you through this entire scenario and how I wrote everything to follow APA style and presenting the results in a journal article that I also presented at a research conference. So that would help you to see, because it's more elaborate than one paragraph. It requires a lot of details for how you need to explain the methodology, the exact rotation you did, and then interpreting all the results and what pattern matrix you determined. If you have any questions or comments, please email me at kelsey.hall@usu.edu or contact me through Canvas inbox.